Hello, everyone. Thank you for coming. I'm going to talk to you today about Sendable. And it seems like it's a bit of a popular topic, given all the extra chairs we've had to go and get. But hopefully by the end of this talk, you'll have an idea of why we need Sendable, what exactly it is, and how you can use it in your code bases to help you write safer code. So before we get going, a bit of an introduction. I'm going to try and drag this out a little bit to make time. I'm Tim, hello. I run a company called Broken Hands, and we do Server-Side.swift training consultancy. So I run training courses around the world on Server-Side.swift and help companies, big and small, ship Server-Side.swift applications to companies and users around the world. However, I am better known as being that Vapor guy. So I'm one half of the Vapor core team, and we're responsible for building, maintaining, and evolving the framework, the Vapor framework. Does anyone here use Vapor? Cool, quite a few hands, excellent. So Vapor is a framework for writing Swift on the server. I'll be doing a lightning talk on it later, but a lot of today's talk is based on the experiences that we've had trying to adopt Sendable in our code bases, and it has been quite a journey. So hopefully all the lessons that we've learnt you can take on board and maybe not spend so much time as we did. I'm part of a couple of work groups for Swift. So there's the Swift website work group, which is responsible for Swift.org. We're responsible for the content and the design of it. So hopefully it's starting to look less like a site that was made last century. And we're adding more and more guides, and there'll be a guide on migrating to Swift 6 coming out soon, written by community members and Swift language members, or the Swift language team members, on how you can adopt some kind of best practices of migrating to Swift 6. So a lot of the stuff today that we'll see will kind of end up in that guide as well. The server work group is responsible for advocating for Swift on the server. So we are a steering group made up of people from Apple and Amazon and Vapor and Hummingbird and other industry members. And we are there to advocate for Swift on the server and deploy engineering hours and effort where we can. So we have really good relations with the core team and the language team to be able to get language features implemented and industry to build packages as we need. I'm also a Server-Side.swift team member at Codeco. So there's lots of tutorials and articles and books and videos on Swift on the server. There's a couple of people at the back who need a chair, I think. So if you are interested, check that out. Obviously lots of iOS content on there as well. And I organise a couple of meetups here in the UK, actually. So if you're based in the Northwest, NS Manchester meets the first Monday of every month. And there's a Vapor London meetup that happens occasionally. And then also I organise the Server-Side.swift conference, which I'll talk about at the end of the talk today, which is a conference based solely on Server-Side.swift. If you have any questions after this and I disappear or I'm busy or I'm answering other questions or something pops up later on, feel free to reach out. You can ask me anything at any point. Well, maybe anything related to Swift stuff, at least, as 0xTim on most of the social media platforms. So before we can talk about what Sendable is, we need to understand why it exists. And in order to do that, we need to go right back to the start of Swift. And back in 2014, Craig Federighi got on stage at WWDC and launched this brand new language to rapturous applause, which was supposed to be a modern equivalent of Objective-C. So all the Objective-C that was being written, all the developers would be able to migrate to this new language. And this new language had four main goals. It wanted to be fast, modern, safe, and interactive. And it's that third one that I really want to nail down to today, which is Swift safety. I'll also get out of the way so people over there can actually see. So Swift has got a number of features built into the language that make it a really good and safe language to use. So for instance, we have optionals. And optionals are a really good feature because it means in Swift, null pointer exceptions just are not a thing. It's not possible to write code with a null pointer exception unless you force and wrap it. And so that's a whole class of errors that you get in many other languages that are not possible in Swift. Swift's got really good memory checking. So some other languages, not naming any names, will just consume a buffer over and over and over again. And you as the developer have to be careful about how you handle that buffer. And we see lots of problems and security vulnerabilities and errors with memory overflows and buffer overflows and memory issues. And those things are not possible in Swift unless you opt into many of the unsafe features or kind of escape hatches that Swift has. So most developers writing Swift code will not be able to hit these issues. Again, another class of errors that are not possible, or at least enforced by the compiler. Swift's got really good explicit error handling. So if you have a function that throws an error, you have to handle that function, function throwing that error. So you have to mark that call with try and handle it some way, whether it's force trying or wrapping it in a do catch or bubbling it up by enclosing it in a function that also throws. You have to be really explicit about where that error is thrown from. And in Swift 6, we're also getting typed throws, so you know which types of errors you're getting. And this all adds to kind of Swift's readability and explicitness about where problems in your code are going to happen. Some other languages, is this function going to throw an error? I don't know. Good luck trying. And you kind of basically have to guess. And I remember writing C# and JavaScript and Java back in the day where everything had to be null checked and everything had to be wrapped in catch blocks because you weren't sure if an error was going to be thrown. And so this all adds to kind of Swift's safety. And then Swift also has really good type checking. So as we know, Swift is strongly typed, it's statically typed, which means that if you're passing around an integer, that is an integer. If a variable is marked as a user, then that is your user type, and it cannot be anything else because the compiler enforces it. Other languages, you just kind of YOLO it. And maybe it's a string, maybe it's an integer. Maybe I can add these two things together and see what happens. Those aren't good things for our code. So Swift stops a lot of these issues. And Swift's whole ethos on safety is to shift everything left. So shift all these problems to compile time and to stop undefined behavior. And I don't mean stop all crashes, because sometimes crashes are the right thing to do. So if you're writing a banking app and you discover that you're running in a jailbroken environment, the safest thing to do is to crash. If you're writing a Swift program for the secure enclave in your iPhones, which runs Swift, and you discover that you're in something that's corrupted or in some state that you shouldn't be in, the safest thing for you to do is to crash out before things get any worse. And that's a legitimate use case. But the whole thing is to stop unexpected crashes and undefined behavior, which means that we know as developers when we're writing our code where the problems are and how to handle that and what the best thing to do is. So yeah, we want to shift all these errors left because compile time errors are good because we get told about them when we try and build our code or when it goes into CI or before we can actually ship our app to users. Other languages, you kind of ship your code, realize you've got a problem in production, and then have to really revert it out. And this is a real problem. And shipping errors to customers and users is not what we want. Which leads us on nicely to data races. So data races are one of the few classes of errors that Swift is still very susceptible to. And many of you will have seen something like this, where you're doing something that you probably shouldn't be doing, and you get an exec bad access error. And this is because you hit a data race issue. So for those of you who don't know, a data race issue is where you have two pieces of code running on separate threads trying to access a shared resource at the same time. So if thread A and thread B try to access the shared resource, and one of them is writing whilst the other is reading, or they're both trying to write at the same time, that is undefined behavior, because which one takes precedent? There's no clear rules for how that should happen. And so this is a data race issue, and this is bad. So the compiler or the Swift runtime will crash your application to avoid you getting into memory corruption errors, basically. And this is a bad thing. And this isn't a problem that's exclusive to Swift. By any means, pretty much every language has data race issues. Here is some documentation for Boto, which is the Python SDK for AWS. And if you go to one of the main sections and then go to a subsection on that page, and then go to the page, and then go to one of the chapters on that page and scroll right down to the bottom of that page on that chapter, and then actually read the documentation and read that one line, you'll see that the single word is bolded, which says resource instances are not thread safe and should not be shared across threads or processes. And it's up to you as a developer to A, know about this, read the documentation, let's face it, that doesn't happen, and then know how to handle it, know how to ensure that you're accessing this in a safe manner and doing it correctly. And we all know as developers, that doesn't happen. We're pretty rubbish at our jobs, frankly. That's why we have a compiler who tells us where the problems are. But data races won't be caught by the compiler. But why? Why can't the compiler tell us when we're doing something that is unsafe with data races? Why can't the compiler catch those errors for us? Why do we have to read the docs? Why do we have to know this kind of inherent knowledge? Why do we have to get it through code review and catch those issues in code review? Why can't the compiler tell us when we're doing something that is unsafe? And that leads me very nicely on to what Sendable is, because that is what Sendable is. Sendable is purely a way of the compiler telling you when you're doing something that is unsafe when it comes to data access, and when you're trying to pass data across different isolation boundaries in different concurrent environments. So, Sendable was introduced in the Swift Evolution Proposal 302. If you have not read it, it's actually one of the more interesting ones of all the Swift proposals out there. It's very detailed and very long and goes into all of the kind of reasons and history around why Sendable needs to exist. But it's part of Swift's journey into concurrency. So in Swift 5.5, we got async await, and that provided us a way of writing nice, clean, asynchronous code to be able to run stuff concurrently in a way that makes sense when you read it, and for the compiler to help us tell us when we have to wait and suspend and be able to write nice linear code. So at some point, we need to be able to pass data across those different asynchronous boundaries and those different contexts. And to be able to do this, we need Sendable, because Sendable is a way of doing it safely. So the kind of elevator pitch, one-line sentence, the VC pitch for Sendable is Sendable provides compiler guarantees of data safety in concurrent environments. And that's essentially all you need to know about Sendable. It's similar to Rust's memory safety in that it's not similar at all, but it has very similar goals. So both Swift and Rust are very similar languages at a high level. They have very clear, high-defined goals of being safe and explicit around concurrency, memory safety, optionals, those kind of things. So Swift's Sendable is very similar to Rust's memory safety. They are implemented in entirely different ways, but they have the same goals of trying to make accessing data in concurrent environments safe. And essentially, when you see Sendable, you can just think as thread safety. So if something is marked as Sendable, it is thread safe. That's the easy way to think about it. Compiler engineers will get very annoyed when I say that, because threads and tasks in Swift concurrency are not the same thing. I know that. Thread safety and Sendable is not the same thing. I know that. But people also say Docker containers and VMs are not the same thing, but they are. It makes it easy to think about. So if you see a Sendable, just think thread safety. And this makes it easy to reason about and understand. And this shifts all of those data race issues that we get at runtime currently to compile time when you compile your code. And it removes a whole class of errors of data race issues so that when you compile your code, you're not going to get, you know that you're not going to get data race issues and your app isn't going to crash because you have different threads trying to access data at the same time when your users are using it. And that's a really powerful feature and very unique amongst many languages. So it makes Swift a really, really powerful language. So how does this all work? How does it work and how can we use it? So you can actually go and look at the implementation for Sendable on GitHub. So it's part of the standard library. It is just a protocol. It's a protocol that you can conform to like any other protocol. It is a slightly special protocol because it has a lot of special hooks in the compiler, but it is just a protocol that you can adopt and use. And it kind of builds up like layers, like a pyramid or like an onion. It's based on layers. Because if one thing's sendable, then everything needs to be sendable. So in order for you to have a sendable type, if your base type is sendable, then anything using that type can also be sendable. And then anything using that type can also be sendable, and so on and so forth. And sometimes it feels like you're just pulling a never-ending thread. It's much like when you try and make something async in your code, and you get all of these warnings because you're not calling await, or if you mark a function as throwing, and then all of a sudden you need to handle all these issues. But this is about Swift being explicit about where your errors are thrown from. So by being explicit, it's a lot clearer when we're trying to read our code a day, a month, a week, a year later about what's going on. So at the compiler level, let's say I have an address book and I'm going to mark this sendable. And when the compiler comes along to check this and compile it, it will actually go through and look at your code. So the compiler will see that you have this type that's called address book and it's marked as sendable. Okay, cool. Let's have a look at the properties. Well, it has a single property of people that's an array of person. So we know that array is sendable because the compiler knows that from the standard library, but let's have a look at person. Well, person is also marked as sendable, so that's good, but let's make sure it is sendable. So we have two types. We have a date. Now date is part of foundation. It's marked as sendable in foundation, so that's good. And then we have this person data. So we go and have a look at person data. Person data contains three properties, a string, an int, another string. Strings are part of the standard library and are sendable. Same with int. And so the second string is also sendable. So because we know all these properties are sendable, and because we meet the requirements of it being a struct, then it can be marked as sendable. The compiler's happy. So because person data is sendable, person now can also be sendable. And because person is sendable, address book is also sendable. And that's how the compiler knows when your types are safe, because it will go through each property and make sure that they meet the requirements of being sendable. So many of the base types in the standard library and foundation are now sendable. So things like dates, UIDs, strings, integers, doubles. You can go and look at the codes in foundation and in the standard library. They're all annotated with sendable. It's very easy. The reason is because most of these are value types. And value types are inherently sendable because of copyright and the protection and kind of the semantics that we get with value semantics. So because if we try and edit something in here, we have to make a copy of it. If you have two things trying to edit it at the same time, they have to make their own copies of it, which is why structs are generally safer than classes, and why Swift has been pushing people to use structs instead of classes for most use cases over the last few years. So value types are sendable, which means that if you have a type that you're using that you want to be sendable, you can mark it as sendable. Problem solved. If it's a struct, no problem, as long as it contains types that are also sendable. In your code bases, structs, if they are sendable, will be implicitly sendable. So by that, I mean that if you have your type person data that meets all the requirements of being sendable, it will be sendable inside that same target or module. So you don't actually need to mark it explicitly as sendable if you want to use it as sendable. If you want to expose that sendability to a public interface, so you're writing a library that has sendable types, you need to explicitly opt into those types being sendable. The reason for this is because it's very easy to make types not sendable by adding a property that isn't sendable, and this will break your API. So in order to keep things stable, it's implicitly sendable internally, but if you want to make it publicly sendable, you have to mark it as sendable and explicitly opt into that. So it's just a little bit of a warning there. If you want to make protocols sendable, well, it's just another protocol. So you can say this protocol must conform to this protocol in the same way that we have used things like codable and equatable and hashable. So in this case, the protocol super awesome thing, will also, anything conforming to that must also now be sendable as well. When you're doing generics, generally generic things can be sendable if they meet the requirements and their generic type is also sendable. Closures can also be marked as sendable, as can functions with @sendable. And this will ensure that any data passed into those closures or into those functions are properly isolated and are safe, and you'll get warnings if not. And that's generally the easy way. So value types, enums, structs can all be marked as sendable. Very easy. That's all you need to do. But I haven't really talked about reference types yet. And there's kind of a reason for that. So in the simple case, if you have a reference type, there we go, that is final, has immutable properties, so they are all lets, and they are sendable themselves, then you can just mark your reference type as sendable. So because you can't mutate anything inside this type, and it can't be subclassed, the compiler knows that this is also sendable, easy to mark as sendable. So you can mark this as sendable. However, Most of us use reference types because we want reference semantics and we want to be able to mutate the properties on those reference types. And this is where things start to get a little bit complicated. So let's say I have my person that I want to make a class because I want to make use of reference semantics. How do I go about making this sendable? And this is where things start to break down a little bit and why people are a bit confused about what Sendable is and how to adopt it. So let's say I have my address book that contains my person that is a class and I want to make it sendable. How do I do it? Well, option one, as we saw earlier, you just whack main actor on it. Problem solved. And this will ensure that any accesses to your address book are isolated to the main actor. Because they are isolated to the main actor, the compiler can ensure that there's no issues crossing isolation boundaries and your code is safe. Option two is you actually use a proper actor. It's the same thing under the hood, essentially. It's just not scoped to the main actor executor. And this is a good thing for most people. So most people should probably migrate to actors if they have types that store reference types, because that's what actors are for. Actors will automatically handle the synchronization of data access inside their actors for you. That's why they exist. So you should start to make use of them if you are not. However, actors aren't a kind of silver bullet, and some people can't use actors because it might break your API. Anytime you access a function or a property on the actor that calls into the thing that is being synchronized, you have to mark it with a wait. And that's a little bit annoying if you have a public API that you need to maintain. So sometimes actors aren't great. Also, if I try and pass non-sendable types into the initializer, this can also cause problems because you're passing reference types or things that can be mutated across an isolation boundary. So you need to be careful about that as well. So option three is you do the synchronization yourself. So in this type here, I have an address book. It has a lock in it, and then any accesses to that lock or to the people that I'm trying to protect are done via the lock. So any time I add a person or get a person or say remove a person, if I ensure that that is done via a lock, I can then mark this with unchecked sendable. And unchecked sendable is kind of like your escape hatch. It's the way of telling the compiler, don't worry, I know what I'm doing. Trust me. It's similar to like a force unwrap or a force try. It's a way of kind of shutting the compiler up. But be very careful about using unchecked sendable because it's very easy to shoot yourself in the foot and cause problems. Because unchecked sendable will stop the compiler doing any sendable checking in that type, which means that if you have issues, the compiler is not going to tell you about them. And in fact, there is an issue in this code. And there's a problem in this code that will cause a data race issue. Can anyone spot what it is?
Where do you unlock?
That's fine. So the with lock function, good question, but the with lock function is kind of a special function that will acquire the lock and then release it when you leave the closure. So it's not that.
Is it that the init is not locked?
Nope.
That can't be locked, right?
Yeah, there's nothing passed in. So not quite, no, but that is a problem with actors with reentrancy. But we don't have to worry about that.
Maybe async?
No, they're all good because it's synchronous. That's not actually a problem, but that could be a problem, yes. It could be, you could subclass this and start changing it. But the issue here.
Where do we index with at the time of calling get person cannot be at the time of it's being referenced?
Yes, I think you're onto the right thing. The issue here is that person is a reference type, which means all the code inside this is actually safe, but person is still a reference type and people can mutate that outside of the scope. So to demonstrate this, let's say I have some code. So I create my address book. I create a person. I then pass my person into the address book. This is all fine, no problem. I then send my address book to some asynchronous function. This is fine because address book is sendable. Remember, we've marked it with unchecked sendable. No problem here. I'm passing it into an asynchronous function. The compiler knows that I'm crossing an asynchronous boundary here. This is sendable. It's all good, not a problem. However, I'm still storing a reference to person here, which means that I commutate the properties of person at the same time as someone who's mutating them inside store address book async. So let's say I do that at the same time that code inside store address book async is trying to read person.name. This is a classic data race issue, and this will cause a crash. So you need to be really careful when you're using unchecked Sendable to make sure that you are actually doing it properly. And if you try and use actors and do this, you will actually get an error. So here, this is the actor version. And in 5.10, if you turn on strict concurrency checking, you get an error because person is not sendable, and you are passing it into this type here. So the compiler will actually tell you this is a problem. Now, in this specific instance, we know that this is actually safe because person is only being passed in, and then we're not doing anything else with it, and we're kind of losing scope. In Swift 6, we get the Swift Evolution Proposal 414 around region-based isolation, and the compiler will be able to tell that that use case is fine, and you will get no warning for it. But if you try and use person after you've passed it in, you'll get a warning because you're not properly isolating your code. As here, so yeah. So in this case, with 414, this is fine because person is not edited or mutated or touched once you pass it into add person, and then you don't use it or store the reference anywhere. So the compiler knows that this is absolutely fine, and we don't have any problems. So how do we actually handle safe mutable values outside of actors and outside of the other stuff that I've just shown you? So you have a couple of options. In the server world, we have something called a neo-locked value box, and you can actually write this with a regular lock as well. And this basically just wraps each property in a lock. So you don't really need to worry about the code there, but if the value itself is sendable, then anything that uses neo-locked value box will be sendable. And then I can change my person, so each of the properties is wrapped in a box. And because I'm not actually mutating that property, I'm mutating the property inside the neo-locked value box, I can make them immutable and lets. And because I can then make it final, and all those lets and they are now sendable, this is actually sendable without any warnings. So this is quite a nice way of doing it. It does, however, provide a bit of a performance hit because obviously any access to name, age, or phone number will have to go through a lock. So it's just something to be aware of. But it is quite a useful escape hatch that we've used quite a lot in Vapor when we've had to make things that should probably have been structs or should be now be actors where we can't break our API nice and safe. Yeah, so I can do the same thing with our address book. So if I wrap my array of persons in a neo-locked value box, this makes address book sendable, and I can pass it around without any issues. The other option with kind of some of the newer stuff is to use the unsafe not isolated thing and actually manually protect it as well. So in this instance, this is very similar to the unchecked sendable thing, where you're using a lock to manually check it, and you're saying that people here is unsafe and not isolated, and this will allow you to access it by protecting it with lock. And this is effectively a way of saying only this property is unchecked sendable rather than the whole type. So in the unchecked sendable type, it disabled sendable checking for the entire class. With non-isolated unsafe, it disables sendable checking for just that single property, and then you can make sure each property is handled. So it's another way of getting around that, and that's available in 5.10. One other option is something like a neo loop bound. So again, this is another example from the server world, but this is essentially similar to how an actor works in that it ensures all accesses to this properties that are wrapped by a neo loop bound are accessed on a single event loop or a single thread. So you can do the same thing with dispatch queues and ensure that you only create these properties on the specific thread and only access it on a specific thread. Otherwise, you'll get a crash. And then that makes it sendable as well. So that's quite a nice way of making non-sendable types sendable by using this. But I generally wouldn't recommend using something like this. You're much better off using a lock or actors or stuff like that. So actors are generally the way to go. But if you can't use actors, use something like this. Okay, so those are kind of some of the tricks that we've learnt over the sendable journey. Paul spoke a little bit earlier about how to start your Sendable journey, but I'll just cover it again for those of you who were in other talks or want to go over it again. So you have two options. If you have an Xcode project, you can go into your build settings and turn on strict concurrency checking. And if you turn it on to complete, this effectively mimics in 5.10 all of the problems that you'll get in Swift 6. So the concurrency checking in 5.10 is now complete. So it will be able to tell you all of the data race issues that you have in your code. Swift 6 is a little cleverer in that it won't have as many false positives, and you have a lot more tools to be able to actually handle these issues. But if you turn on strict concurrency checking in 5.10 and you have no warnings, or you fix all the warnings, then in Swift 6 you're going to be absolutely fine for Sendable. If you're writing a Swift package, you can do it with the experimental feature in your package manifest. Because obviously if you're writing Swift packages, there's no Xcode project. So this is a way of turning it on with that. And when you turn it on, you'll see you might get some warnings. So this is Vapor just after we turned on strict concurrency checking. We had just a few warnings, as you can see. But what you'll find is that actually many of those warnings are duplicates. So we have kind of three main types in Vapor, which is the application, a request, and response. Once we made those three sendable, almost all of the warnings disappeared. So don't be too worried by the number of warnings, because generally it's the same warning over and over and over again. So you'll see you start to get some warnings and errors. So you will actually get some errors if you're doing stuff that's really unsafe. So this was an example where we're doing something really stupid of passing an immutable type into a closure that can then be mutated outside. This is really bad, and so the compiler just says no, even in like 5.8, I think this was. Most of you will see warnings like this, where you get reference to captured via application in concurrently executing environments is not sendable, or capture of configuration with non-sendable type HTTP server configuration, blah, blah, blah. So in this instance, once we made application and configuration sendable, so configuration was very easy. It was a struct. We just made it sendable. Application took a lot more work. All of these warnings disappeared. So you can just start manually churning through these warnings. I think I have a slide on per target. I can't remember if I do. So in case I don't, we go back quickly. So when you turn on strict concurrency checking in Swift 6, you will actually be able to enable it per module in your app. So if you have a really nice app that's split up into lots of different modules, you can turn it on in each individual module by setting the language version to each individual module, rather than having to migrate your entire app at once. So that's a really useful feature, so you can go through it slowly. I'll just skip through. Our journey to Sendable was quite difficult. So it took me almost a year to land the first pull request in Vapor to adopt Sendable stuff. The reason for that was A, I didn't know what I was doing. B, no one else did either because it was brand new. And C, a lot of the helper functions like the neo locked value box that I've shown you didn't exist when we started this journey. So we kind of had to try and make it up as we went along and feed back to the Swift team and the Neo team about those problems. In earlier compiler versions, we managed to crash the compiler a lot. This isn't that uncommon for Vapor. We tend to crash the compiler a lot because we do some really questionable things, I'll say, to make it nice for people to use. But this was a conversation on the Swift open source Slack that generated a fair few discussions between myself, Gwyn, the other Vapor core team member, and some of the Swift team about why we were getting this crash and how to work around it. Thankfully, all of these have been fixed in 5.10, so most of you shouldn't have any issues when you try and adopt. So I do want to talk about maintaining your API quickly. So if you are writing iOS applications, you can mark stuff sendable. You can add sendable requirements to closures without any problems because it's your app, and if you break the code, you have to fix it. That's not a problem. If you're writing packages or APIs or libraries that you then provide to other people, if you start making breaking changes, you have to release a new major version. And that's something that's not always that easy to do. With Vapor, we have to be very careful about maintaining our public API. We obviously don't want to break it constantly because you're going to piss some people off. So we want to keep those APIs stable as long as we can. And we actually managed to adopt Sendable and have 0 warnings with strict concurrency checking without breaking our API, which is why it took so long. And it's a bit of a pain. It really is a pain maintaining your API. I'd much rather write application code at those points. But hey, if you are writing library code, here are some nice little tips and tricks to ensure that you keep your backwards compatibility. So the first one is app pre-concurrency. So if you have a function, so for example, this is our function in our WebSocket library called onPong, because in WebSockets you have pings and pongs that you need to handle. We had to make this callback sendable so that we could ensure that it was safe. Anyone then adopting that, who has already adopted that, which then upgraded to the latest version, would immediately get a warning saying that the types that were passing in were unsafe. And this is a bit of a pain if you're just pulling in an update of your libraries and you all of a sudden get these warnings. So if you add the app pre-concurrency annotation to the function, it actually tells the compiler that this function exists before concurrency was a thing. So if they are doing stuff that isn't strictly sendable, don't tell them about it. It's fine to hide the warnings. If you turn on strict concurrency checking, you will still get these warnings. But if you have the default concurrency checking warnings, you won't get these warnings. So that's partly a reason to help you with your APIs and partly an example of why you should turn on strict concurrency checking to complete so you actually find these issues. But it's a really handy little feature to make it easier for your users to adopt your APIs. If you have dependencies that are not fully updated yet, as Paul explained earlier, you can use the app pre-concurrency import, and this will silence any sendable warnings for types inside those libraries. So if you have a dependency that hasn't been updated yet, and there's nothing you can do about it, it's a nice way of silencing these warnings. And the really nice thing about this is, as well, is that when your dependencies actually update and fix those problems, so when console kit fixes all the issues inside that are not sendable, you'll get a warning from the compiler saying that pre-concurrency is no longer needed. So you know when your dependencies have been updated properly. So it's a nice way of keeping those, like that audit there, to ensure that it's still, so you know which dependencies haven't been updated and which people you need to pester. This was something that we hit quite often. We have a number of classes. So this was from our request class, where we have a method. It's public. It's a mutable property, but we need to make it not public, or we need to make it not mutable in order to make our types sendable. But how do we allow people to still mutate it? We did this with a classic bait and switch. Our method then became a computer property, which we then accessed via a lock, and the internal actual property that's stored on the type is just underscored. And that's a really nice way of maintaining your API from a public point of view whilst making stuff sendable. Because computer properties are computer properties, so they don't need to be immutable for sendability requirements. So, to recap, Sendable provides compiler guarantees of data safety in concurrent environments. So think of it as thread safety, but it is a way of the compiler telling you when your code is not safe. It's not that complex to actually think about and reason. It's a bit more complex to actually implement. There are still a lot of proposals going through the Swift evolution process at the moment for Swift 6 to make a lot of the issues that you'll get in 5.10 easier to manage. So for instance, region-based isolation that I showed earlier, where the compiler can tell that you're not using this reference type past this point, this is actually safe. That's coming in Swift 6. There's another one around usability of global isolated types. There's another one, and another one, and another one, and there are a lot of proposals still going through the evolution process right now. Things are changing a lot. These are the evolution proposals that I found last week, purely based on Sendable for Swift 6. There's a load of others for other types. So things are still changing. So keep an eye out on Swift.org, because the migration guide, when it's finally finished, will contain all of these examples on how to adopt and migrate your code bases for many of the common types, especially with things like Swiftui and Swiftui views that don't really work with Sendable at the moment. So don't worry too much. Keep an eye on it. Try turning it on. WWDC is just around the corner, at which point Swift 6 will be out, or at least the previews and the new Xcode, where you'll be able to turn on strict concurrency checking in your app. You'll be able to use the Swift 6 language mode in your app. So I think to answer Paul's question earlier of how do you turn it on in Xcode is wait for the Xcode 16 beta. and I'm pretty sure you'll be able to turn it on then. But it is coming. So I do recommend that everyone at least tries it once dub happens and sees how many problems you have in your code. As Paul mentioned, and as I mentioned earlier, you can keep your code at the 5.10 language mode. So you can use the Swift 6 compiler and the 5.10 language mode. You don't have to opt into Swift 6 straight away. But I do recommend it because even though you don't have any warnings or errors in 5.10, your code is still unsafe. The warnings aren't new warnings. They're just telling you where you're doing stuff that is currently unsafe. So you can stick your head in the sand as long as you want, and you don't have to worry about all these things that are errors. So in Swift 6, all of the warnings you get in 5.10 will become errors. So your code will not compile. So if you have deadlines and managers breathing down your neck and need to get stuff shipped by September, you can keep it as it currently is, but your code is still unsafe. So just because it doesn't it still compiles doesn't mean your code is magically safe, just as a warning. And that's everything. Thank you very much.